Okay, hi everybody. So I wanted to discuss this topic because it's very important and it goes beyond uh, individual issues or issue with people in the space. I mean, these issues are important. There is a history behind, but I want to avoid to discuss personal issues or people's issues and focus on the science. Because to me that in the end is what is important. And, it's important, of course, that people, if they work hard for many years, they are appreciated and recognized. But it's that is a secondary matter. So the issue is in regard to the fact that I'm noticing that this quantile model is getting some attention, and it's great because if a quantile model, and that should be called actually the quantile power law model or the quantile regression of the power law model, will get attention and people will learn about Bitcoin and learn that is a power law that follows this particular pattern. It will be great. It doesn't matter who is working on the model, if Sina, PlanC, Fred, anybody, if they contribute, they add something, they explore improvements on the idea is great. But taking it from somebody that worked 12 years on the topic, adding some window dressing or just some further analysis, and then avoiding the word power law completely for political or even economical reasons because you want to appropriate it and want to claim you are the author of this new model when it's just another way of showing the same thing, maybe with some additional benefits. It's misleading. So let's leave alone the personal issues and damages to whoever made the model in the first place. It's misleading to the people, to the public, because you don't explain where the model comes from, what are the premises, what is based on. Okay, so I want to correct that. I already done it in the past and posted, but I want to emphasize because I have a few things that I can show you. um, how saying just quantile, it means absolutely nothing. That is what I'm trying to show you here today. That quantile, you can make quantile regression of many different things, and you will get different models. Okay, and in fact, and instead you get what Sina and PlanC show only if you use the power law framework, and that should be mentioned. That is my point here. And when people then use their models and they say, oh, the quantile model, I have seen, for example, Cointelegraph, at the table of different type of predictions, and they mentioned Sina quantile model. Well, it's a power law, okay? If Sina made a nice calculation, a nice graph, okay, but it should still mention, because in fact, there was in that table, I don't have this table here, but you can find it online. There was a column that explained the modeling or the framework or the assumption, and you say simply quantile regression of what? It means nothing. So this is what I was trying to. I'm going to explain you here. Why if they should mention is a power law. It's a power law model. Okay, so what is a regression? So basically, the regression is a statistical method where you're dealing with some data, right? Like many times, in particular with Bitcoin, we want to show how data relates with each other, right? Usually, I have done this with hash rate. I have done this with addresses. You can show relationship between Bitcoin and price and addresses, and time, hash rate and addresses. You can do it with many different things. But usually, we have time. In this case, when you're dealing with something that is some value and changes in time, we call it a time series. It's a technical term. And a lot of financial data is disorderly, doesn't seem there is a precise pattern, but other times it seems there is a pattern, and the pattern can be temporary, where you can use some kind of temporary relationship. Is always, when you are modeling, you're always simplify. You're always trying to make something simpler than what it is, because you're trying to catch the essence of what you're modeling, and you say, look, it looks mostly like a line. It looks mostly like an exponential, and sure, it will not be perfect. That is the entire point. You're trying to simplify the data. You're trying to recognize some kind of general trend, and whatever deviation from this trend, it's understood as a form of noise. Now, it could be that you have more than one signal and you are just modeling one part of a signal. Like with Bitcoin, for example, Bitcoin could have a power law part, and then these bubbles could be understood as an additional signal that are sine waves. But the dominant signal, it will be the power law. Now, there are also different ways of thinking about data. My favorite approach, that is here where I could be different from Sina, for example. PlanC is mostly asking ChatGPT to give him answers, and I'm trying to avoid personal attacks, but what happens, and also it is mostly asking ChatGPT. There is nothing wrong with asking ChatGPT. It's great. Everybody can do that, and I'm for everybody being as what is called citizen scientist, right? I would love everybody to be a citizen scientist, but there is still a difference between somebody like Sina that studied to be a professional in the field. He's not a physicist. He's a business person, but business major. But he has to study statistics for what he does, because he analyzes trends, data, right? So, and I could have some philosophical differences with him on this idea that statistics is the only way to describe Bitcoin. We can discuss that in the end. I think statistics is one of the tools. The main things that the power law give us is that it seems there is something more than just statistics. There is some fundamental principles related to network, related to scaling, that makes Bitcoin more like a physical system than simply in physics we use statistics, but there are underlying principles that gives us patterns, equations that are more powerful than just statistics. Because if it was just statistics, the power law will lose a lot of its predictive power. That is, to me, is very important to emphasize that the fact that we claim that, and this claim could be wrong or right, but if a claim is right, then it's much more powerful, because we are saying there is some kind of underlying mechanism that tell us how Bitcoin is evolving in time, and we can use that to be more certain. You never be certain 100% in science, but it gives you much more confidence in the predictive power of a model. If it is only stats, or what you can say, well, so far it has behaving this way, you cannot really say that it will continue to do that. Like you can say, well, if it continues to do this, then this will happen, right? It will follow this kind of statistics, but there is almost no guarantee that it will continue to do that. And with the power law, this is one of the things that I try to emphasize more and more and more, that is supposed to be causative. We say what the causes are that are producing the power law. It's a network. It has this network property. So this network property come not from the statistics. Usually statistics for a physicist, the last resort. Like, we don't know what is going on, so we are trying to understand the statistics, and maybe from the statistics we go back and find a cause, we find a mechanism. So this is where I could be very, very kind of butting ahead with Sina, for example, mostly from our background, from our conceptual framework. I think mine is superior, because I'm telling you, I have something more than just statistics to understand Bitcoin. If he claims that it's all statistics, again, because of his education, his framework, etc., then he kind of capitulates a little bit. I don't think, the fact is that I met Sina when when I started to get attention for the power law, and he actually came to my rescue a couple of times by actually explaining to people that I had a deterministic factors in the model. And he was okay with that. He even told me that he worked with physicists and he understood where physicists are coming from, and that in understanding economics, physics can have an advantage from simply a pure statistical approach. So, but we can discuss that because it's very important. I want to show people that this is why the power law is such a big deal, because it's a mechanism on how Bitcoin works. But let's go back to what a regression is, because we still use these tools, right? This is how we identify the power law using regression. But you have to understand, and I will try to drive this point more at the end, it's just a starting point. It's not the end point. The starting point is, okay, we found this power law through regression, and we don't stop there. It's basically like you're doing archaeological finding. You dig, you find something, and then you're trying to understand it, you're trying to explain it, you're trying to put it in a context. It's much deeper than just finding a line. That is one of the criticisms that many people give to the power law, because they are confused, and that confusion needs to be clarified. So anyway, regression, right? So you find this data, you have this data, you have usually, it can be more than one dimension. In fact, there is nothing, in theory, you could regress over 15 dimensions, right? It's more abstract because you cannot visualize 15 dimensions, but mathematically you can do it. But usually we have graphs where it's 2 dimensions or 3 dimensions, right? And most of the time with financial data, we focus on 2 dimensions. So maybe price and time, right? And we want to find some kind of a pattern. We have this point, that could be basically the price every day. And then we think that there is a pattern, and we want to use some mathematical tool to verify scientifically, not just by drawing something with your hand. We want to find some scientific way of identify, validate this pattern, maybe calculate some variable that tell us how good the model, this line, this pattern that we found represents the data, the underlying data. And there are different tools, different metrics that you can use. And so, there doesn't have to be a straight line. It can be a more complex curve. Humans like straight lines, and they are very easy to identify. And also the mathematics behind them is simpler. So if we can represent the data as a straight line, is much better, because we can, from an intuitive point of view, recognize the line. Then we can try to fit it like a line. The equation is simple. The statistics is simple. So that is one thing that we try all the time. So in physics, they trained us. So let's go to the next slide. To plot different type of graphs. Okay. So the first graph, so basically it's almost like when I was teaching my class, my classes when I was a professor, we had lab classes where people needed to learn how to actually take data, and then, you analyze the data. Many times we reproduce classical experiments, things that people did in the past, and we wanted, because this is what science is, right? You want to verify what other people did in the past actually is real. That is what, is the difference between and almost any other field of human activity with science. You can reproduce. If you don't believe that the Earth is a sphere, you can actually go through all the steps that people follow for millennia to actually show that. And there are these sometimes that you find on YouTube, silly people trying to do experiments like that. If they do it properly, they actually get shocked because they prove themselves that the Earth is a sphere. But when you have a data, you have to plot it in a certain way. So the first thing you try is always to plot the data linearly. So you plot the price, for example. You don't do any modification. You just take dollars, right? and then you plot it versus time linearly. And you see if there is some kind of a straight line, like in this case, right? We're not looking at Bitcoin data, but just generic data. Imagine I did an experiment. I have a bunch of data. See, when you do data, usually you sample one thing at a time. Right now, we have some digital methods where you can sample hundreds of thousands of times, hundreds of thousands of times per second. So, in physics, we do a lot of experiments like that, where we have enormous quantity of data, and they are reproducible. If you certain experiments, you can do it in your tabletop, on a tabletop, right? But with financial data, usually you have data that come from some kind of source, right? A record of transactions in some exchange or whatever. Now with Bitcoin, you have several exchanges of what people talk about when we are trying to make this model. There are different sources. I use TradingView sometimes, for example, and there is something that is called all index history, and it's basically kind of an average between all the different exchanges, right? So prices are slightly different in different exchanges because people do these transactions locally, but people are very aware of what is happening in other exchanges. It used to be where in the old times you could actually make a lot of money by taking advantage of these differences between the different exchanges. You could trade in one exchange and buy Bitcoin at a cheaper price and then selling it in another exchanges where the price was slightly higher, right? And if you wrote a code that could do this fast enough, you could make a lot of money. But because a lot of people do that, the price differences now are relatively small. But you could use averages, right? So you could use averages of data points, right? So you have these data points, maybe they represents averages of price on different exchanges. And if the Bitcoin price look like this, right, where X is our time and Y is our price, then you will look at this data. Imagine there was no red line there, and you will say, and sorry if I say things that are trivial for many people, right? I'm assuming that maybe you never took a class like this, or maybe you took a class like this a long time ago and you forgot about some of these things. So I'm trying to go to the basics, right? So of how we do these things. Like if I was teaching class when I was a professor, I will say exactly these things. I will tell you, look, we collected several points. They are points because you want to kind of take a snapshot of whatever phenomenon you're describing at a precise time, and you're measuring the value, measuring two values, right? Now, the precision of these values it's never perfect. There is always some error in how you measure these things, right? But we think that these errors are relatively small, right? And so you're measuring these values at a precise time, within some level of precision. It could be 2 decimal places, 5 decimal places. It depends what you are describing. With prices, it doesn't make much more sense if you're using dollars, for example, to go below the cent, right? So maybe 2 decimal places because we are describing in cents. And they will be scattered because you are measuring them at different time. Now you notice here that the time between these observations, it's constant, right? But in theory, you could do it at random times too. But nowadays, because we digitize everything, we like to have very precise times, consistent times between the samples. And if you're doing it with Bitcoin, for example, you're interested in the long-term trajectory, you could do it with weeks, months, whatever, but days is good, right? Because days is a good measure of how Bitcoin changes over a long period of time. Some of these things are, more like an art than a science, right? What should I use days? Should I use week, etc.? You can do it many different ways and then compare. But so this is the idea, right? We are a bunch of points. I don't know how many points are these, maybe 20 or whatever. And you're looking at this graph, right? If a red line was not there, you could, it's kind of difficult to say what it is, but it kind of looks like a straight line, right? So we're trying to say this is what we are doing, right? I know that sounds so trivial, but people say, why do you even explain this? Because I want to make sure that we understand each other. It does, right? It's not a bad representation. Could it be that there is some slight bending to this graph? Yeah, to this data. Yes, it could be. Could it be that it's just by chance? I will say it's very difficult that this pattern is just chance. It could be that for a short amount of time it looks linear and then it does something else later on, right? That is another issue. But at least over the period that we are analyzing, it does look like it's kind of linear, right? Now, it's not perfect because you can see that if it was perfectly linear, all the points will be on top of a line. They are not. There is some scatter, right? That is what is going on. Now, is that noise? Is it due to our imprecision in the measurement? Is it because maybe there is a linear tendency to go up, but it's not perfect? There is still some disorder, some noise in the signal, right? It's never noise, because if in theory, the reason why the price went up, there is a reason, even if it is simply because there were a bunch of people who wanted to buy that day and another day they wanted to sell, right? There were more people selling than people buying. There is a reason why that happened. It's just that we don't know what that reason is, right? We don't know if we, if we had this incredible wave of understanding why people make decisions and we could get data from every single person on their cellular phone or whatever, maybe somebody could make a crazy model where you can predict every single ups and downs. We don't, right? We are not yet there, or hopefully we never be there, right? So, but there is some kind of general tendency in the data to follow this linearity for whatever reason. And so if you see something like that, the first time you always plot y and x linearly, it looks linear. I'm going to make an assumption. This is where the modeling comes from. Okay, so I want to explain this very explicitly to people that maybe this you not do this as a job every single day. This is what we mean for modeling. You are making some kind of a model. Model. Think about a model, right? When you have a little soldier model, right? Like I like, these are soldiers that I was playing when I was a kid. I have here because I love romance and I'm nostalgic about this. This is a model, right? It's a model of soldier because it's like simplification of what a soldier looks like, right? It's a model. It's a simplification. It's in this case is even in terms of its size, right? You're reducing it to a particular scale, and you're making a model of a data, right? You're simplifying it. You're coming up with some kind of a hypothesis of what kind of behavior these data follow. And in this case, we are making these assumptions. You see, this is my assumption. This is my model. This is my model. It's a straight line. If you don't remember from high school or middle school when this was explained, when you took some classes, right, about math, it's a relationship. It is linear because you have y here, right? So this little symbol there means that is your model. That is your theoretical model. And you have x, that is your real data. So this is kind of an abstraction, and this is the real data, so the time data. And you're saying is a straight line because there is some kind of a slope. This b1 represents the slope, how steep this curve, this line is. And then this represents, right, because if x is 0, b0 will represent when basically x is 0. So it will be when the straight line crosses the y-axis, okay? And only with these two numbers, b0 and b1, you characterize one unique line. You find this line. It's uniquely represented by these two numbers. You need two numbers to represent a line. It's a two-dimensional object. You need two data points, right? And the goal of a regression of this statistical model is to find these B0 and B1 given the data. Okay, so you are trying to find these B0 and B1. So if there is an algorithm, in old times people will have to do all the calculation by hands. Nowadays we have computers. You press a button, you give it data, and the algorithms goes through its steps, and the final goal is to give you B0 and B1. Once you have B0, B1, then you can ask a computer, draw me a line with this B0 and B1, and this line. So this is what regression means. It means to go through all these steps. Now, the way that the particular steps are done depends on all the assumptions. And in this case, for example, we work in this space. This is how we call it. The space in which we operate, right? It's a linear space because we have both the y and the x that are linear. We are not doing any modification. We take them as they are. And if you do that, then straight lines will look like straight lines. Exponentials will look like very fast moving up curves, right? Same thing with power laws, but they have differences in how they behave. They will look like J curves, they go up. But a straight line will look like a straight line. And this is the equation, and this is your goal, right? So here what is represented is the error. So what this formula means, the error, so the errors between the model, that is the red curve, it is an idealization. It doesn't even exist, because notice, not a single point is on that red line. So how is possible that this red line is supposed to represent the behavior of our price when none of the points is even on top of a line? It can, because it's an idealization. It says, here it is, the general path. Yes, not a single point will be on that. It could be, but in this case it's not on that line, but it's still a representation. It's the best we can do in trying to simplify the data and say, look, there are variations, but in general it seems we are going in this direction. You see how this work? And if you don't understand, you should be able to ask me questions, and I can address some of your questions. And then you define what is called an error. You see the error is here. You basically draw a line. Now, you could do it in a different way, right? You could do it in a way that you find the minimum distance from the curve, but it's not what is done here, right? So there are different ways of doing it. In this particular case, the error is you're measuring, you go down, you find the point, you go down along the constant x, and then you find this distance. How big is the distance between the predicted y, that is this one. So this little hat here means that is the prediction of my model. My model says y should be here, but the real y of that particular x is actually here. So you measure the difference, and the difference, this difference can be positive or negative according if you are below or above this line, and so you're measuring that error. Then part of a regression method, the essential fundamental part, there are several parts, right? First of all, the space where you're operating, and then the model that you're using. In this case, we are deciding that we want to find some kind of a linear relationship, and how you define the errors. And the next step is, what is your goal? What you are trying to achieve? Okay. In this case, for example, if you use one of the most used type of regressions is called the ordinary least regression, okay, or least square regression. Why is called in this way? Because, and you can read all the steps. You can use Grok. You can use Google to explore this if you want to understand it. But basically, you are assuming that there is this linear relationship, right? Here it is. In this case, we are writing a slightly different A and B instead of B1 and B0, right? But you should be familiar now that is the form of a line, and we want to find this A and B, right? Where Y is we call it dependent, because we are saying the time is passing by and time creates, it's creating a particular value of P, because we are saying that somehow there is some relationship between the price and time. And as time passes by, we should see price going up as a function of time. Time is basically what is determining the value of price. I know it sounds crazy for most assets, right? Because it's not like that. They are much more random. But this is one of the things we claim for Bitcoin, that it's time what determines the price of Bitcoin, empirically. Then that actually why it grows in that way, etc., is also due to other things like addresses and the Metcalfe law and so on. But in general, we are saying, well, just let time pass, and that will tell you what the price is. So one is a dependent variable, y, and the other one independent, because you are not controlling time. Time is moving by itself. And so the component of doing regression will be the model, right? This ya plus bx, how you're treating the data, how you're measuring the error, and then what you do with that error. In this case, you see here what we do. I tell you about this symbol, okay? What this means is, it looks complicated, but it's not. It means let's measure the error for every single point. This I means all the points. So 1, 2. So you're going, imagine you have some kind of a loop, right? You're going and take the first, it's like a recipe that you're giving to the computer. The computer follow your recipe. Take the first data, in this case price, subtract it from the model. Now the model, it's abstract, so it will be, you will use this is why maybe you didn't like when you take math, right? This alphabet soup. It's useful because you don't know yet what A and B are, so you write this expression with these theoretical values A and B, and then you write down the real value of the price, and you're subtracting it. You will still have these variables, but then the next step is to find this variable through mathematical methods. But the idea is you're subtracting all the different, in theory you could do it where you test the different values of A and B. You say, okay, let me do it many times. Let me start with some random value of A, some random value of B. I do this process. What is this process? You're subtracting, and then you're taking the square. Why you're taking the square? This is why it's called least square. You're taking the square because you don't care if the deviation from your model is positive or negative, right? And if you take the square of something, if it is negative, you basically eliminate the negative sign. It's going to be always positive, right? If you take the square also of a negative number, it's going to be positive. And of course, if it is positive too. And then what do? You sum them, because you want to see this symbol here means sum. And this I to n simply means sum through all the n. So if you have 30 data points, start with the first one, right? It's like, imagine this is a recipe. You have I1, then I is 2. So this is where basically the real value and the predicted value, right? You subtract. Every time you go to the next point, you subtract the difference. You calculate basically the error. You square it. And then this simple, now I say, why don't they write it in a simpler way? Because if you are used to this symbol, it's much simpler, right? It's a more compact way of writing it. This symbol is a sum. It's a total sum of all these differences. So you sum it, and that gives you the total error, how big this error is. You can imagine what I want to do next, right? I would like to minimize this error. I would like to find, so that the goal of this algorithm is to find A and B that satisfy this requirement that I want this to be the smallest possible value. So imagine I did this. So there are more clever way of doing it in this way, but I could do it, with brute force. Imagine if you know a little bit of programming, you write a for loop, and you give me a range of possible A's, right? A, remember, is the intercept, very large range of A's, very large range of B, the different slopes that this line can have. And you go and you do this through these calculations. You do it many times for different choices of A and B. And then you say, okay, among all these, give me the one that has the smallest possible error. some total sum of errors. So that could be a way of doing it, but you will have to do a lot of loops. You will have to guess a big range of the values. It's not the most efficient way of doing it. People came up with optimization, with different techniques to do it. And actually turns out that if your assumptions are simple, like you're just saying, well, there is a straight line there, I'm not doing anything complicated, I'm not using, because you don't have to just choose a straight line. You could have a model where, what if I add a square term? It could be a plus b x plus c square, right? You could actually add more terms, so a cube, etc. As you make it more complicated, you lose that beautiful power of having something simple. This is why we like straight line. It's one of the simplest possible relationship between data. If there is a straight line, why will you want to make it more complicated? Unless it doesn't look like a straight line, then you make it complicated. But if it is a straight line, and even if it is not, perfect, you still stick with the straight line, right? And it turns out also, if you look at a short interval of data, almost everything looks like a straight line. It's actually what calculus is based on, right? That you can always find some kind of a portion of the data, if you decrease the interval, that kind of looks like a straight line. So in that case, when you're dealing with a simple model like this, that is a straight line, actually there is a formula. You can find a formula. You can use calculus. It's actually one of the things that people teach in calculus, how to solve this problem. It's one of a nice, beautiful application of calculus. And naturally, when you do that and you go through the steps, you can show there is a very, very precise solution. You don't have to just try random values of A and B. There is a solution for the problem, and the solution is this: that basically you take you get B, the y-intercept, through this formula. If you want to understand this formula, again, remember this is a sum, and is the sum of what? Of the products between all the differences between this x value and y value. So basically, this average value of x and y, you take the differences, and then you divide it by the square of these differences. And A, it's once you find B, first you find B by doing these calculations. So these are simply the averages, the means of X. So you take all your data point, right? All your times, you take the mean of these times, you take the mean of the Y of the prices, you subtract every time. In this case, we are not Xi will be separated by equal intervals, but it doesn't matter. And then you subtract all these guys, you subtract all these guys, you multiply, you sum, right? It's a very simple recipe. The computer can do this in in a fraction of a second. This is why doing the linear regression, it's one of the simplest way. You don't even need a sophisticated code. You just write down these two equations, and the computer can do this in a fraction of a second. And once you find B, then you can find also A by subtracting these, right? This is the equation. So it's very, very simple and a beautiful result. And then this is what gives you this thing. This is what gives you this curve, okay? Now, what we teach to our students is that if you don't find immediately a straight line between the data, between Y and X, go to the next step, because many data, if they are not a straight line, many times, in particular when we are dealing with physical data, they can be an exponential. They can be an exponential, right? What an exponential is a process, because all these equations, for a physicist point of view, if you're thinking about the world as a physicist, there is some kind of mechanism behind that determine the relationship, okay? The fact that it is linear means there is some kind of proportionality, like when you have, in the equation for a gas, right? pressure and volume, right? Or pressure and temperature. And this can be inversely proportional, directly proportional. For example, with temperature, you increase the temperature is going to increase pressure. There is some mechanism. What is the mechanism in that case? Temperature is the velocity of a molecule. So if you increase the temperature of a molecule starts to move faster, they bombard the walls of your container more violently, and they create more pressure, right? So people didn't know that. Eventually they understood what was the mechanism. But for a physicist, the fact that there was a linear relationship between pressure and temperature was kind of an indication that the two were related through some kind of a mechanism. So it's very important to understand this. It's not just some kind of random thing. There is some reason why there is this relationship. So with an exponential, if you have an exponential relationship, it means that there is some kind of process where one quantity grows very fast relatively to the other, and basically some kind of a percentage rate. So, for example, if you have a bank account, right, that gives you 5% interest every year, if there is such a bank account, probably not, but they give you 5% every year, right? You are going to take the money that you gain, you're going to add it to the initial capital. Say you started with $1,000, and after 1 year you will have 5% of that. You add it to the $1,000, and then now you have a little bit more money than $1,000, right? You have a $50. So you have you start with 1,000, now you have $50, and then you have 1,050. Now you're calculating next year 5% of that. It will be more, right? And then every time you have a bigger and bigger sum, and you're taking the same. That is what is critical about the exponential. It's the same rate of change, right? So if you have this same rate of change and this compounded over time, it will give you an exponential. That is what is typical of exponentials. And there are many processes in nature that follow this exponential. So we teach our students to find another straight line. And what will be that straight line? Well, if you take now the log, right? So you have the same graph, but now you're taking the log of y, and you take the linear of x, it will look like a straight line. So if now your data start to look like a straight line, in the beginning it didn't look, right? Imagine I had something that was a curve. It is this curve. Now it's a curve, it's not a straight line. You will not want to fit a straight line through that data, like in a linear model. You're looking for some other type of relationship, right? Now, there are some codes that will be able to find that relationship without you plotting it in a special way, but it's better if by plotting it in a special way, that is a simple operation, now the pattern is clear. So imagine I started with something that looked like a curve, and then I do this, we call it a transformation. We do a simple transformation. Now, instead of plotting the y, the price, we plot the log of a price. And now if the log of a price looks like a straight line, and you can show yourself why the case, because basically the log kind of cancel that exponential, right? If I have something that looks like y equal exponential of x, I take the log of y, so both sides, log of exponential cancel, and you're left with the x. So it will look like a straight line. And it's nice because you see how easy for a human eye is to recognize a straight line and say, oh, it seems there is a straight line through the data. And now you're doing exactly the same steps, exactly all these steps using least square regression. But now, instead of taking y, you're taking the log of y. You're feeding to the computer, in fact, you can call it big Y. You can always change. This is why we love the alphabet soup, right? And many people get frustrated by it because they don't understand it. But once you're used, it's actually cool because you can, I don't like to write log of price. Well, call it big Y, Now fit that big Y to these algorithms and you will get this straight line. But now that straight line represents an exponential. If you go back and draw that straight line in a linear graph, it will look like an exponential, okay? Now, if your data doesn't look like a straight line in a log linear graph where you're taking the log of y and the log and the linear x. The ultimate trick that we do in physics is taking the log of y and the log of x. And now if it looks like a straight line, it's a power law. So that is what we have explained since I started to show people that Bitcoin is a power law. We have explained this many, many times, and I don't know if people understood it and they follow all the steps. But it's very important to explain these steps because otherwise you don't understand what we're doing. So it's part of being a good analyst and serving the community if you explain these things, because when people don't look at just a nice chart, I know that most people don't have time, they look at a nice chart, they click, I like this chart, has nice colors, has a nice table, it's useful, and you click the like button. But in my case, even when somebody makes something else, right, a model, etc., I always want to understand. I don't know how it feels to be somebody without a math background, but even if I didn't, like when I look at other things in other fields, I always want to understand how this was derived, where it comes from, not just, okay, it's there, I'm going to click, right? So this is the idea, right? Hopefully it's clear. So it's important how you prepare the data before you do the regression. The regression is just a tool. It's something that they are using to help you to find in a scientific mathematical way that can be arbitrary, because they say, why did you do this? Why do you try to minimize this? It makes sense. You're trying to find, right? Let's try to understand what this least square regression is trying to do. Remember, ideally, it will be nice if all the points fell on this line, right? Imagine we have a very good data with small variation. And then I say, well, I try to find a line that fits most of the data, right? It's going to be, you could try even to do it manually, right? But it will be very arbitrary. Or say, I'm going to move when roughly my eyes tells me that, the distance of these points from the line is small, right? That will be the best possible, we call it best fit, right? But you're finding a mathematical method to to represent this process, and it needs to make sense mathematically. It can be arbitrary, because I could say, well, what if I want to take the distance here, right? Like a line that is perpendicular to the line. You could do it that, or you could say something else. You can come up with some other criteria. Maybe you want to give more weight to the point that are below. So you want to give maybe a bigger weight to the negative point, because it's more important that you minimize the negative deviation than the positive equation. That could be a choice, and this is why you will have to explain that choice. If you make that choice, look, I'm using a very particular way of finding this best line by minimizing the negative distance. You have to explain it. Otherwise, what you do, it's not clear to people, and you're showing and sharing this what we do as an analyst or influencer, whatever you want to call it. We are supposed to give a service to a community, and if you don't explain it, it's almost like worse that you didn't do anything at all, because it can be misleading if you don't explain it, right? Some people use this chart and make some decision. They decide to buy more Bitcoin or sell Bitcoin. People actually use them. And so it's very important, to explain as clearly as possible what you're doing. You don't have to do it every single time, but, there has to be a place where you explain your premises. Okay? So, and there, like I said, there are many different ways. So now, recently, this thing about the quantile seems to be very popular, right? I think I can explain in a moment the logic behind the quantile and how it's different from the least square. But I can tell you why I think some people find it useful, or some additional information to what we get normally is because of this, because usually, so here is some data, right? I'm going to find some kind, it looks like, if you this data is very good, it kind of looks like flat, right? That is another way of representing the data. It looks like flat, nothing's changing much. But if you kind of squint, there is some kind of a trend, right? A little bit upwards, and a lot of scatter, a lot of noise, right? That is also the other thing that I was telling you philosophically. I come from more this field that is called signal processing. Half of my dissertation was on this field. It's more like an engineering way of thinking about data, where you have what are called signals, and there is noise, and there is filtering, different way of eliminating the noise. I love this approach much more than a simple statistical method. People like Sina don't know about these methods. They are focused on the statistical property, while a physicist knows both the statistics and the signal processing. It's some additional, more, I think, deeper understanding of the data. But the usefulness of a quantile. In fact, to be honest, we don't use much in physics or engineering quantile. I was aware of it, but it's more like something that an economist will use. Econometric models use this thing, and has some pro and cons, right? Like everything, I'm okay. It's one more tool, fine, great. And I think the appeal of it is this, right? Is that because with Bitcoin, right? When we look at these models of Bitcoin, we have a power law. It gives us a clear general trend. But then the question remains of, well, is there a way of characterizing these deviations, right? One of the best deviations that we find that is always super consistent is that support line. And that support line, you can calculate it easily. You don't need any sophisticated method. It looks like you take the general trend, calculate it through the least square, and then you look for a 60% deviation. Now, there are more sophisticated ways of doing that, but why finding sophisticated things when you can do simple things? Unless you want to do it in many ways and then show, look, I did it in 10 different ways, I found the same results. That is valid. So one of the first things that I like about this quantile method is that it finds that, in fact, all the data below a certain level, they are all power laws. They look like all the power laws. And then the level that tell us the support is something close to 0.03 percentile. And I will tell you in a moment what these percentiles are. And so there is perfect consistency between the quantile model or the quantile regression, because it's not really a model. It's just a way of doing that regression. The model is that component explained you in the beginning when you decided, does the data look linear? Does the data look an exponential? Does the data look like a power law? That is what is your real modeling, the modeling that is meaningful, okay? Because again, talking with PlanC, sometimes he plays these semantic games, say, well, but I'm still modeling, it's ridiculous. No, you're not modeling. The only modeling part is when you decided that this is a power law. That is the only thing that requires two brain cells. Everything else is just pressing a button or asking ChatGPT. There are many different ways of doing regression. So what is appealing, I think, is that it has a natural way of looking for deviations and finding, let's say, objective way and not arbitrary way of setting up these levels. So that is what is attractive. Now, is the only way to do it? No, because I could take these and then calculate, I can look at the distribution of the deviations, what are called the residuals, and then say, I'm going to find 0.1 standard deviation, 0.2 standard deviation, 0.3 standard deviation, up or down. And we have done that many times. I had many graphs where I have a bunch of lines like these. That is just another way of determining the deviations. Now, is this better than that? I don't know. There are pros and cons. they are completely consistent in determining the support level. The support level, it's the same. It doesn't matter if you use quantile, Bayesian. We tried one time, I tried it with 10 different regressions, and they were giving us always the same result. That is more meaningful. Again, if you're a good educator, pointing out to that is more meaningful than say, oh, in my quantile model, it's stupid. It's just another way of doing regression. And the best way when you're comparing different methods is to show what are the pros and what are the cons, what we can learn from one method and what we can get for another. They're just methods, unless you have some, ulterior motives and you want to put, your tag, and you're saying, oh, this is proprietary. What is proprietary? Quantile method has been invented a long time ago. There is nothing proprietary about that. It's just another, okay, good. You mentioned the quantile among many regression methods. By the way, we came up with this discussion in a group where we were discussing exactly this topic. How should we represent these deviations? And you ask ChatGPT and tell me, what are the different ways of doing regression? It will tell you. It makes a list. In fact, this is exactly what they did, and we can show in a moment. We can go through them. Okay, here is a long list. You can ask to Grok, please tell me how many type of regression there are and what are the pros and cons, and give me some examples. This is exactly what they did, and we can go through them in a little while. It's just another way of doing regression, but it's nothing particularly better in one model versus another, unless you're looking at specific components of where one method is better than the other. But I think this is where the appeal is, right? That you have these levels, and they come in a more natural way than other methods. So what is behind this? First of all, what do we mean for quantile? So you take the data, and usually, you can do it in a historical fashion, right? You will say, I'm going to take the first year of data. I'm going to take the second year of data. And then that is another thing that you should do, because there's one way also to show that doing these over time has been very consistent, right? We do it with the other method, and that is actually one of the big results. In fact, Sina contributed on one of these results using not the quantile, actually the least square method. It shows that if you use the least square method, we have done it before him, but I was very happy when he did it, because here there is this professor of business that made a test. He has, he consults people on these kind of things in the past, and in a show where Fred was interviewing, he actually had a demonstration that, it's kind of inconsistent initially, because the data was dominated by the large bubble that we had in the beginning, 2010. And that bubble is so big that dominates all the data and they skew it. But as you add more data, the fitting becomes more and more consistent, right? With the quantile, actually, you do have some problems that I will mention in the beginning. It's not that consistent, actually, because think about the logic. Logic is this, right? You're taking all the data points, and then you're saying, okay, computer, just line them up. Like is a process that is called sorting. So you sort all the data points. These are the prices, right? Imagine all the prices. Imagine you do it now, right? You're taking all the prices that we have. We usually take data since 2010, because this is when Mt. Gox opened. So we take all the data from when we started to have reliable data from exchanges. So you take all the data that could be averages from different exchanges, when you say sort them out from the smallest value. So it doesn't matter time, because when you're doing this sorting, you're not looking at time, right? Because it's possible that we had a peak here, and then we went down, and then some time later we went higher. And so, this peak, this lower in between, happen in between these two high values, right? So you don't care about organizing them in terms of time. You organize them in terms of value. So you sort them out, right? You sort all the values from the smallest to the highest. And then you say, find me the 10 percentile. So basically, 10% of the data. So if you have 5,000 data, so you're going to look at the first 500 data, right? Only 10%. So give me the first 500 data in this sorting, okay? It's an interesting way of doing it, right? You're losing some information that is the time organization of the data, but you're focusing on how big the prices were, right? And so you're taking these guys, and this is your 10 percentile. If you take 20% of these, that will be your 20 percentile, 30 percentile. You can see, right? You're getting more and more of the data as you go to larger percentiles. Okay, so this is what we mean for percentiles: bigger and bigger amount of data after this sorting. Now you can imagine this sorting changes, right? If I did it 10 years ago, the sorting will be different, not just the value, because now you have more value as you add more time, but how the order will also change. The order changes all the time, because you could have value now that were lower of some value 3 years ago. Okay, so the sorting changes. It continuously changes as you add more data. But in general, you expect some level of consistency, right? Because it's not that crazy. The variations are not that crazy. Anyway, so then what do you do with these quantiles, right? Okay, and this is where maybe the biggest difference between the two methods comes from. It is this equation here, okay, that tell us, remember, we come up, okay, so, and here is not explained because, all right, we saw the data, but what is our data? This is where, again, remember when I was explaining the different components of modeling, your modeling comes from. It's not that you're using the quantile method, because that is just a method in deciding what you do with this error. That you can come up with 10 different ways that are kind of reasonable. Like, remember when I say I'm going to give a little bit more weight to the negative points versus the positive points. It's not the normal way of doing it, but I could come up, because maybe I have some reasons to do that, with that method, and it will be a completely valid method. You could call it negative weighted. You can have a different name. You could weight it by the volume. You could weight this. You could do a line like this, weighted by the volume. Every time you measure this error, you give you have some kind of a factor, and you multiply this factor by the volume, because maybe you say, look, if it was a spike, but it was just generated by very, very little volume, I'm not going to give it a big weight. I'm going to give weight only to changes that add a lot of volume. You could do it in many different ways. It's not that you're coming up with a new model. It's just a different way of describing the data. Your model is that you're thinking there is some kind of linear relationship in the data. So even when you do the quantile model, you have to start with some assumption. What am I going to feed to my algorithm in terms of X and in terms of Y? And I show already here, this is the graph, that if you feed the different things, your result will be different. If I tell, okay, my X is linear and my Y is linear, I'm going to get this garbage. So it doesn't matter if you use quantile, and this is where this deception, and now I'm calling it as it is. It's a deception just to use the name quantile. These things sometimes are attributed to ignorance. The rivalries that say don't attribute to evil what can be explained with ignorance. It's a mixture of the two, because I think PlanC doesn't understand very well. Maybe Sina does up to a point. I noticed that he also understand some of my arguments of this when I try to, but more subtle. Like, for example, in that case, is it a good idea to represent, even with this idea that we are dealing with a power law, the upper levels? Is not. That is a separate argument, but it's more technical. But in general, beyond the technical thing. It's something really, really, really basic. If I feed price and time directly and I do a quantile model, I get this. Does it look good? No, because I get a bunch of straight lines. Remember, we're trying to find all these levels, right? So all these colored lines are different levels, different quantiles. And the quantiles look like spread like this. They are a bunch of straight lines because we are trying to feed, we are trying to feed something that is non-linear. Bitcoin price is non-linear. Everybody knows that. We went up in a very non-linear way, and there is not a straight line there, but the algo, because you are instructed it to use lines, if you're feeding X and Y as linear values, it will try to find lines. And I even tried to discuss this with Sina, and he doesn't. I don't know why he doesn't get it. I don't know. Okay, you have to understand that this is what is. You cannot survive as a physicist. I'm sorry if I always mention this physics superiority of every other scientist. There is something true on that, right? It's like we are the Marines of science. There is some level of eliteness in being a physicist and anything else. You really need. I know because I taught physics. I saw people that had straight A's in biology and business and everything, and they will take a physics class and they will die because it requires thinking. You have to think. You have to understand what you're doing. That is a requirement in physics. You cannot do things in a mechanical way. You have to understand. You have to understand the process because it's about processes. It's not about final result. It's not remembering things. It's about understanding the logic of what you're doing. So if you're thinking about the logic, you're feeding X and Y, and then you're saying, and we will see how it's also slightly different in terms of finding this line. It's not just a straight forward least square. It's a little bit different. It's kind of a weighted least square. It's still least square, but weighted, and we will see how that works in a second. But you see, this is the result. So this is quantile. I could say quantile model. Which quantile? Quantile, what are you regressing? Okay, are you using a linear model? If you are using a linear model, this is what you'll get. It is not what Sina or PlanC shows. They don't show this because it will be a ridiculous model and everybody will laugh at them. There is no straight lines through the price. I mean, you can draw them. This is what the algo does because you ask it to do. The algo is not clever. It's not going to find the fitting unless you're telling it which kind of fitting you are looking for. If you're telling I'm looking for a linear fit of the data, this is what it will give you. It will try to do its best. You see how it found a range because it finds a range because of the sorting of the data, but it's completely ridiculous range, right? So, and this is if you feed the log of price and time linearly, then what you're doing, and you're saying, and now find straight line, because this is what you're doing when you're asking for the regression. You're still finding this straight line, but in different spaces. In that case, is trying to find straight line in this space where now there are ways of modifying the quantile model where you make it non-linear, but the simplest application is always linear based on certain data. So if it is linear in a log linear space, then the lines are not the lines anymore like they were here. They are, hopefully now you know that because I have repeated so many times, it's an exponential, right? If you're taking the log of price and keep X linear and you see straight lines, it's an exponential. And so all these straight lines that the algo finds are all exponential. It's trying to find a bunch of exponentials through Bitcoin price. You see? Is that a good model? No, because look at this, right? In particular, in the beginning, it looked like crap. It doesn't really fit what was going on. It doesn't follow really the behavior of the price early on. And yeah, okay, here you could say, well, for a while, but remember, I can take any data and I can find always a place where it looks like kind of straightish. The important thing, the beauty of a power law, that it does this incredible work of finding a general trajectory that works from the early data all the way to today. That is the power of a power law. And if we continue to do that in the future, we will have to see. But that is where we come in and say, whoa, this is something that is not due by chance, has to be due to something deep. It's a mechanism. Okay, so it's not a good model. It's not a very good model at all. Notice, right now, for example, if this model was right, we will be at a support level. We reach a bottom, and we are at the bottom for a long time. I don't know if there is anything to learn from this model. I think it's a bad model. Okay. Now there are even ways of calculating. This thing called the R square. You can calculate the R square. It's not the only quantity, but there are many other there are tests. You can do more sophisticated tests, information theory-based tests. You want to compare these fitting with a real exponential and tell you if that it is. And this model fails almost all these other tests, right? It's not a very good model. Yes, for a while look like we're going up exponentially, but like I say, you can always find a straight line through data, because everything reduces to a straight line for a small while. Even here, look at, here we're following a straight line. Was Bitcoin straight, going up straight during that time? Not really, it's just our eyes. They want to find patterns. And if it is just over a small amount of time, it will look, you can always find a straight line. But look at this. This is when you are feeding to the power law the log of time and the log of price. That is the promise of the power law model. That is where you do the modeling. You're saying that beyond the data, there is this power law, and the power law will be revealed by taking the log of time and taking the log of price. If you feed it in that way, then you will see a bunch of power laws. And in fact, this is what it does. All these straight lines, these curved lines, are because a power law in this type of graph. If I did this with the log, and I don't have it in my slides, but I can post it and show you. If I did this in a log graph, these curved lines will look like straight lines, and the exponentials will not look like a straight line. Okay, so different spaces reveal different patterns, and the most natural way to reveal the power law is to take the log of time and the log of space. If you don't do that, and you're still representing power laws, because every single of these equation here is a power law. Every single of this line is a power law. If you're representing in this way, it's not obvious. That is also part of a deception. They never show you the log graph. And if you talk with PlanC, it says, oh, but people don't like it. No, it's not true, because people like it many times when you show. They want to know as much information as possible. So show both ways, right? Show it a simpler way, because yes, we like linear time. We like to look at linear time. It's simpler to understand. But whenever I did a log graph, people like it because they see that it's a straight line and it looks weird, right? And it seems that there is something behind that straight line. If you want, you can just show both. I should have showed both, and I did it most in this way to show you it looks exactly like what Sina and PlanC show, and they call it only quantile regression of power law model. This is how it should be called, because otherwise it could be this, it could be that, it could be something else. It's the premise is that you are doing the power law, because people will be confused and we will not understand what you're doing if you don't do that. It's not good. It's not a good contribution or good educational post if you try to mislead people. And there is a reason. It's not that, it's a long ass way of writing what the model is, because they could put it in the comments, they could put it in the description. They do it on purpose. They are doing to this, to do, maybe to separate from me. Fine, whatever, they can do whatever they want. That we don't have to be always friends, but it's not just that. They want to claim it's a new thing. It's not. And it has problem anyway, because we have shown many times that it's not a good idea to start to fit a bunch of power laws as you go at the higher level, because it turns out, and maybe I can have another video because otherwise I make this video too long. We can do a part 2 of this where I show you why. I already did some videos like that, but we can go again and revisit, in particular at the light of what I'm describing here. It's an okay way of doing it. It gives us some information. So it turns out, just to give you a preview of what we can discuss in part 2, there are 2 modes. There is one mode where Bitcoin is below this blue line. This blue line actually is the least square. I plotted also the least square. But it's very similar to the 50 quantile. It's almost indistinguishable from the 50 quantile. If you take 50% of the data, right, you have 50% above and 50% below, and then you're applying the quantile, you get something very close to the least square. It turns out, if you want to be technical, the 50 percentile is the median, what is called the median, and the least squares gives you the mean. But again, it's cool to do it both because you get additional information. If you know what are the pro of one method, the pro and cons of one method versus the pro and cons of the other method. But say, oh, this is superior, that is the other thing we do. This is the ultimate model. It's stupid. It's absurd. It's misinformation. And so this is why I need to correct it, being actually the creator of the model, and they are copycats. Okay? So anyway, the main concern is, given there are these 2 modes, so there is a mode of a data point. Me and Steven have shown these many times. We have done many studies using physics and many different methods. We show that there is a clear difference between the behavior of Bitcoin when it's below that power law, the median or the the mean, and when it's above. It's really 2 different behaviors, and they should be described in 2 different ways. If you simply start to plot a bunch of power laws, it's not clear from here. You will have more clear. See if I have actually a graph of that. Yeah, I do. So let me actually add this graph. So you can, I plotted it, but I didn't add it to this slide. So it will take me just a second. So be patient. But, we can have another show where I go a little bit more in the details if you're interested. So we are going a little bit more technical. I wanted to keep it very general. So, but let me give you a preview. Okay, here it is. So if I show the same graph above, right, this is the power law quantile model where I feed the log of time and the log of price. I get this. If I go see what is the difference between this guy and this guy, is that this guy is the same equation, the same lines, but now they are shown in a space where it only take the log of price, but they keep the time linear. You see? But if I now take the log of time, this is what I get. I get a bunch of straight line because I'm trying to fit. It's not that the algo finds these power laws as ultimate thing. It finds them by itself. It finds them because I told them to find a bunch of power laws. You see? The question is, then that is our job as an analyst, because the computer can do it. I think ChatGPT, I'm curious, I could feed it to Grok and see without giving it any information. Grok, I start to like Grok more than ChatGPT, by the way, because ChatGPT kiss your asses too much and I don't like it. PlanC loves it. I'm sorry, but I couldn't resist. But anyway, I don't like when the computer agrees with me. It doesn't agree. I don't want to agree with. I want the truth. Anyway, so the problem with this is all these lines that are between the lowest quantiles, right? So when you just remember what quantile means, you're collecting only few data, right, that are at the bottom here are the smallest values for the price, right? So it's after you do this sorting. And so it's trying to fit only this data when you're saying, show me the lowest quantile. It only fits the lowest data. And and then, you start to add more and more data, and so it starts to fit more and more data as you go higher. And up until you arrive to that list, to that blue line, they are all parallel to each other with small little variation. That means this idea that there is a power law, that is another way of showing it's not just some kind of arbitrary thing. A big chunk, I think it turns out it's about 55% of the data, it's actually following these power laws in almost perfect. If I eliminate, so it will be a non-arbitrary way of selecting the data, right? So of eliminating outliers. You could take off, right, and not even show them in the graph. It will look like crazy. It will look like a perfect straight line. We have done that many times in the physics of Bitcoin show. It looks scary, very big gaps, but how come the price goes back there following this, green area channel, whatever you want to call it. When you go above, the data behaves in a very different way. Even if you look at the distribution of the data, it's very symmetric below and not symmetric above. The deviations tend to be equally distributed on the left and on the right when we are in that regime below the blue line. When we are above, we tend to have these long tails. That means high deviations are more likely. And so the statistics are very different. And Sina should understand this, even from a statistical point of view. He claims, it's not a good idea to treat data differently. You can. If you have a distribution that has two peaks and it's basically the sum, basically there are two processes. Maybe it's not used to think in that way, because in physics we see many times there are like Stephen calls it the core and the turbulent flow. It looks almost like when you have turbulence. If you have an airplane and the airplane flies at a relatively high but not super fast velocity, you don't see a lot of turbulence. If the airplane start to go very fast or it goes through some kind of disturbance in the air, you start to see a lot of turbulence. You can absolutely model these two regimes with two different approaches. You can, in fact, you should. This is trying to understand the data versus I'm applying some mechanical method, because this is my problem with some of these people that have a different type of thinking about the data. They are more by the book instead of really understanding deeply the mechanism behind the data. This is why I think this physics approach is much superior, because we are always trying to understand. That is our motivation. We want to understand. We want to know what the causes are. And that has to be something very different when the price starts to go above that median, and it behaves in a very different way. And the statistics reveals that, but you don't stop at the statistics. The statistics are a tool to tell you something is different. So you see, if I model this upper part with a bunch of power law, notice what happened to this power law. They start to change the slope. It makes no sense, because if there is a scaling behavior that covers many order of magnitude, it doesn't make sense that when you go there, it's a different behavior. It's an artifact. And the artifact is because there are two things. There is the overall power law, and then these deviations start to decay exponentially. And you can demonstrate, because if you subtract the deviation from the trend, you can show that they decay exponentially. You need to go deeper. And then there is a way of recovering the quantile model. We will cover this in another episode, part 2. And I can show you how to still apply the quantile model, but now you separate what you do to the core and what you do to the upper levels. And it's a much more consistent, much coherent model. But still, not saying that is a power law quantile model is misleading, because people don't understand what you're doing. They should show this picture, show that you're finding a bunch of straight lines through the log space, and it's just another way of showing the power law through layers, right? Through different layers. and how you model the upper part, it's something that it's up for debate. Let's say, okay, it's more technical, and it's a minor point. Is no the essence. The essence that is a power law model. Is not quantile is the technique that you are using to show that we are dealing with power laws, and you're showing you are dealing with power laws because they look like straight line. So you're missing completely the point. It means nothing. This simply because people don't understand these things. They look at a graph like this. It looks nice. It looks pretty. PlanC is a marketing genius, so he knows how to make them nice and use the right color. He even told me that he studies these things. That is what is great for it, and there is a space for that. Great, right? Fantastic. But don't cheat people, because it's not even me. It's cheating people by not telling them you're dealing with a power law, that your model is a power law model, and that is what you're plotting. And these are power law lines. There are people that don't even want to deal with the power law because whatever psychological reason, and they like this because they think it's something else. It's not. It's a power law. I don't know how many times notice all these are quantiles. This one is like quantile power law. So tell people that is the power law. That is my point. But I told you that I was going a little bit deeper in explaining you how the quantile works, right? Because beside these levels, how do we find this level? How these levels, beside the sorting that we mentioned, there is one more detail. The detail is, remember I told you a very important factor is once you feed the data, right? So that is really where the modeling comes from. You decide, am I dealing with a line? Am I dealing with an exponential? Am I dealing with a power law? Am I dealing with maybe a polynomial? Because in theory, you could say, well, it's neither of these things. It's actually, there are higher terms. There is a x square, there is a x cube. The problem with adding x square, x cube, etc., is that it turns out that you really can model anything if you add more and more terms. That is something like, again, that maybe we can explore another time. This is why people don't use a lot of these polynomial models. Is like, again, kind of a last resort thing. If you cannot find, so what do you do? Like, and I did it in one time when I was trying to model the relationship between price and global liquidity. If you do it over a short amount of time, it's not that short. It's last 10 years, right? So if you plot, actually, yeah, since 2014. So if you take the last 10 years of price and global liquidity, it looks like a power law. But if you go farther, then it doesn't. So and then there are no other tricks, like I told you, right? You do linear, exponential, power law. There is nothing else that is simple after that. So you have to make it more complicated. That means adding parameters, so you can add squares and cubes. And it turns out there is a theorem called the Taylor expansion that basically says you can fit anything you want. It doesn't matter how complicated, even just crazy noise, by adding more and more terms like this, polynomial terms. You can do it with sine waves. That is the basis of anything that is digitized. I use sine waves to extract all the frequency from a signal, and then you reconstruct it through frequencies. In this case, another approach where you use polynomial. So you start to use, you go with a straight line, then you add a quadratic, then parabola, basically a cubic term, a fourth term. You can add more and more and more, and it starts to look more and more like your model. The problem with that is you're not finding anything general, because it's just a trick. Remember, modeling means you're thinking that there is some kind of general behavior that it will last, notwithstanding the deviations. Over time, it will still follow that general path. And if you do it in this way by adding terms, you're not finding that. You're just finding the local. You're fitting. This is what the concern that many people have. It's this overfitting. You're overfitting. It means you're fitting it too much to the past, and you're not distinguishing what is a real signal and what is the noise. So you're trying to avoid that. I did it one time with global liquidity. Now I prefer to do it using the power law and keeping the data simple. But that means there is not something really too fundamental between the price and global liquidity. There is some kind of relationship, but it's not as simple and fundamental like the power law. So that is where the modeling comes from. When you decided what am I going to use to express this signal? Where is my signal? And Sina and PlanC are absolutely using the power law as their signal. Now, there is one more technical difference that I need to explain, and then I will take some questions, if there are questions, about how the quantile model treats the data, right? So it's a very clever way, and these, tells you also where maybe some of the pitfalls of the quantile method is, and where maybe some of the strength components are. So basically, what they do. So for each quantile, so this is where it's called the loss function. So remember, when we went to the when we're discussing the least square, we said we need to know what to do with this error, right? And the idea was, let's take the square of these errors, let's sum all the errors, and then let's try to find a way to minimize this error. And that it will give us some kind of best fitting line. Under this criteria, we need to know what is trying to do, what best fit means, right? Best fit is arbitrary. Best fit according to this method, right? That is logical. That makes some sense. And you can go deeper and say, okay, by doing this, what do I get, right? What are the good sides of it? What are the strengths? What are the weaknesses? The way that the quantile model does it is this. So this is how we deal with the error. So you take the quantile, this symbol tau, right? So simply means whatever quantile you're dealing. Remember, we draw one line at a time. So the quantile regression is not just one line, it's a bunch of lines. You can draw one line. You can say, I want to show only the 10 percentile. I want to show only the 50 percentile. If you wanted to choose one line that really represent most of the model, you will take the 50 percentile, right? But usually the beauty is that you can have many lines, and then you can show how the data spreads, right? So you go through each line, and for each line, right, this tau will be the percentile. So let's say 10 percentile, right? And then you do something similar. Notice I'm taking the difference between my theoretical model. My theoretical model will be, for example, in the case of what the power law quantile model means, it's you will take a power law, that y is a power law. It's the log of price versus the log of time, right? This is what this y hat means. You're taking a power law, repeating, you're taking a power law, so it's a power law based model, and then you're taking the differences of the price. So actually, in this case, it will be the log of the price relatively to this model. And you weighted, so it's basically a weighted, it's like a least square, but weighted with one more difference. It's not exactly the least square. I will tell you why, because remember how we were minimizing the square? Notice what they do here. They take the absolute value. So this is what it means, the absolute value. They don't square it. And there are some technical reasons why they take the absolute value versus the square. They give you slightly different way of dealing with the data. It's not that deep that it's worthwhile to go. You can watch some videos on. There are plenty of videos on YouTube on quantile regressions. It will be for somebody that really wants to go deep on, small technical differences. But it's kind of the same, because taking the absolute value, basically you're saying, I don't care if a value are positive or negative. I care about the absolute distances, but the critical part is this weighting, right? So let's see what, and then, so I'm having two parts of the data. I'm going to give different weights to the data. I'm going to give, these to the data here. This is what symbol this means, right? Notice if you go, do you remember it still means sum all these guys, sum all these differences. But here, basically, there is almost like an instruction of how to treat the data, right? Which data? Well, the data y1 above this y hat, right? And remember, y hat is the model, right? And this is below. So basically, we are treating the data that is above a quantile and below a quantile differently. In this case, tau will be 0.1, right? Because this is, you're expressing this tau between, it's a number between 0 and 1, where 10 percentile is 0.1, right? 100 percentile will be 1. So 0.1, so it's a small number, and you're multiplying all the data above the model. So everything that is above a 10 percentile, you give it a small weight. So you're still including it in your data set. It's not that you are fitting only the data that are sorted below the 0.1 quantile. You're also including the upper level data, but you're giving it small weight for the low quantile. Notice what happens when we go, when, if it is 50, you will treat equally. So this is the data below and above. So you will give more weight when you have 0.1 quantile, you will give more weight to the data below that quantile. So you give it 90% weight and everything else 10% weight. If you go to 50%, we will have equal weight, right? Because it's, see, the other component is 1 minus tau, right? So if tau is 0.1, 1 minus 1 is 0.9. So you get 90%. And when you are, tau is 0.5, same weight. As you go above 0.5, notice what happens. This number becomes big. So imagine I got 0.95 quantile. This will be most of the weight for all the data. It is just a little bit. You have a little bit. Think about Bitcoin, right? When we have our model, we can go back, right? Here, it will be only these little data points up there that are part of making this red curve, right? Because, yeah, okay, you include also the rest, but you're giving it, it's a lot of points, so we are going to have a dominance, right, in terms of by the time you average them, etc. And so you're averaging a lot of points. So it's not completely idiotic way of doing it, but you're emphasizing the weight of the upper quantile. And this is one of the reasons also why these slopes start to change, because you're giving a lot of weight to the fact that you have these huge big deviations, and so they change the slope of a power law. So this is a critical thing. As you go to higher and higher quantile, you're starting to give a larger weight. Is it a reasonable way of doing it? There is some logic behind. Is a way of they claimed, we'll have to go through all the details why it is, that is kind of reducing the influence of large artifacts, larger data that doesn't fit the rest of the data, outliers, but it has its pitfalls, okay? It's not an infallible method. The fact that you are using this kind of weird or maybe well thought weighting system, it's useful in certain situations and not useful in others. In fact, like I told you, there are many different type of regressions, right? So we can look at what are the pros and cons of different methods. So for example, I like the linear regression, mostly because it's simple, it's easy to interpret. Like that is the other problem with the quantile. What really these upper levels mean? I ask Sina 1 million times. He never gave me an explanation, because if you plot them in this way, what does it mean that we have power laws from, so the slopes, just to give you an idea, these slopes, they go basically from 6 all the way to 4. What these slopes 4 means? They are power. First of all, notice also that eventually these lines will all cross, and the upper one will go below, and it's completely. See, in physics, we are used to see many times mathematics because we use it as a tool. And there are times where you apply it and it gives you a result, like, okay, you could have a certain situation where the result is negative mass. And they teach us to say, look, take a result that makes sense physically, throw away the other one. But most of the time, it's a good idea. There are other times where some scientists say, why should I throw it away? Like, for example, Dirac, right? He had some mathematical calculation, and he was getting these electrons with positive charge. And we knew that electrons were negative charge. And he said, I don't want to throw it away. Maybe there are positive electrons. And it turns out, yeah, there is such a thing like antimatter. And he was lucky at that time not to throw away this result and take it seriously, and he discovered something amazing. And you can do that, right? That is part of exploring, like say, okay, why should I constrain myself to this idea that there are power laws only with one slope? Maybe there are a bunch of power laws that have all kind of different slope. But then you have to explain it, because what Dirac did, he said, well, there is, and I think even actually turned out that, I don't remember completely the story. I don't think actually took it. If I remember well, the story actually initially didn't take it serious. And then somebody discovered that we did have these antimatter electrons. They had a positive charge. And then he kind of went back and said, see, I kind of predicted it. I think this is how the story goes, but you can correct me. I don't remember 100% the story. I will check it out later. But, sometimes things that don't seem, we call them non-physical results, right? They are non-physical up to when you discover other things, and then they become physical. You revolutionize physics by discovering antimatter, these weird things, right? Where you have the same particles with the opposite charge, right? You have a negative proton, a positive electron, and so on, right? There is even an anti-neutron, believe it or not, even if it is zero charge. But anyway, and you can find out why. But yeah, so I'm not, if these things mean something, these power laws mean something, then you need to explain it. What is the significance? What is the meaning of this power law? You cannot just say, oh, it's some statistical thing. No, it is not. I'm not enough. I'm not satisfied. I'm saying the power law at the core represents some kind of scaling behavior, and I'm giving you a physical explanation that has to do with the network property of Bitcoin, etc. And then you have these deviations where we deviate, and we have this turbulent flow. I have a full understanding, or at least I'm trying to give a full understanding of how Bitcoin behavior. If you're saying there is this power law, what are you saying, that they scale in this way? What are you saying? Give me the explanation. Give me the interpretation. Interpretation is more important than just the modeling. Modeling, anybody can do modeling. The important thing is the interpretation, what it means, what are the consequences, what are the causes. They never give it to you. Also, because they never show this graph, they show this graph, it seems a little bit more reasonable, because it seems that they are kind of converging or diminishing, but they don't show you that eventually they will cross. That makes no sense. So, they never go to trying to explain the interpretation. So that is one of the problem with quantile regression, that doesn't have a easy interpretation. It's very complicated to understand what is like. Sometimes, yes, like for example, at the bottom, basically we are finding the power laws. The quantile model completely agrees that there are a bunch of power laws there, and they are all consistent up to 50 percentile until the contribution of the large deviations starts to come in, and then you see some different behavior. The power law is still there, but in addition, there are all these other things that change the behavior of the data. That is the meaningful interpretation. But in general, but Sina will stop there and say, well, this is what the statistics say. No, that is not what the statistics say. The statistics say there are two distributions. It's a bimodal behavior, and you're not accounting it, and you're just throwing away the information because you like that is a consistent way of representing these deviations. But because you're focused on form, while I'm focusing on meaning. I care about meaning. I care about understanding. I care about mechanism. So that model, it's okay, is one more tool. Sometimes I show it because it's nice and it looks okay, but the best usage is kind of saying, when you're looking at these deviations, it's the best case scenario. It cannot be better than that, because when you are talking about the price, like today, Fred had this post. The model says we are going to revisit 95. It doesn't say that at all, first of all. And in fact, these 95 quantiles start to be really extreme values. It's almost like saying, if Bitcoin continues to behave like in the past with these really, really large deviations, and it, because okay, again, right, if we really want to understand, it does allow for a little bit of a decay, but that decay is undervalued. It is an overestimate, it's underestimation of what, and it doesn't look very clear from here, because you say, well, it still does a very good job, right, in trying to go through all these peaks. Not really. If you try to push it further, you can see that it's underestimating the exponential decay. There is like an exponential decay through these peaks. Now, does Bitcoin have to follow this exponential decay? No, but there is no reason why it has to follow these. For example, you see how we are leaving behind these, like the fitting here is much above the first peak. Okay, if I included only the 3 peaks, it will go through that peak. So this slope at the top is changing, because remember, again, what we are doing, we are sorting as we get more and more data. We are sorting in different ways. So it's an illusion, and again, I will have to have a second episode to explain you all these things. Right now, I don't want to tell you, trust me, but I can tell you I did the work, and I can show you that it overestimates the peaks. So when you make tables like this, they say, it could be, such and such value if we reach this quantile. That is, if we reach this quantile, that is probably unlikely. So when Fred says, we are going to go there according to the model, no, the model doesn't say that. And in fact, actually, it's kind of a crazy scenario, best case scenario. If we go there, we could go there if Bitcoin starts to do more or less what it did in the last bubbles, and it does account for a little bit of a decay, but not much. It's underestimated. So you can still use it, because I am in favor of showing. If you we have a Patreon program where we have right now, I think 13 different indicators, and the quantile model is one of them indicators. We have that model too, because it's one of the way that you can look at the data and say, okay, what if we had a best case scenario? Where we go? So you can use it in that way, and it's always better to use more than one approach. It's all, these models are all based on the power law, but they are a different way of showing the power law, different information that you can get from the power law. So the quantile model has that function. There is a better quantile model that we will discuss in the next episode, but it's not the end of it all. This is another way of showing, see this, if we had a data like this, we spread in this way, right? It could be simply that we have one single power law, one, in this case is linear, one single line, and the deviation. So that could be one interpretation, right? Imagine there is data like this, and the data is linear. It continues to grow linearly, but also the dispersion, how much distance the point. So maybe there is more noise as time passes by. There is more variability, but we are still oscillating around a single way. Is this a good way of representing what the data does? And I don't know, not really, because what these lines represent, right? It's not a good way of showing that there is some kind of increase in the noise. You will find these lines because it's trying to do the best thing. You're saying, find me a bunch of straight line by including more and more data and giving that weight, and this is what you will get. But there are limitations. There are times when it's a good approach, other time it's not, right? So here, you can list. We can go through these pro and cons. To me, the linear regression starts always from simple. If simple does it, use it as your point of reference. Start from there. And the linear regression does a very good job in finding the general path. And in fact, it finds, for what concerns Bitcoin, also the support where you can you do a linear regression of a log, because that is still the critical matter. You take the log of the price and the log of the time. You do a simple linear regression. You're getting the mean. That represents the fair price. It represents the reference price. And then you can say, well, but I don't think that is really the reference price. It's just one way of representing it's an abstraction, but the abstraction is that there is still a very predictable, very general pattern that Bitcoin has followed for 16 years. It's a very valid model, and it's simple. It's easy to understand. Now, here the criticism, assume linearity. Yeah, assumes linearity of log if you're feeling log. Okay, and that is okay because that is assumption that yes, there is a power law, and a power law is a straight line in a log graph. So that is okay. Normality, not really. I mean, it works better if the data is normal. Normal means equally distributed on both sides. And this is why if you eliminate the peaks by not arbitrarily by using some method, in fact, you can say, okay, give me all the only the normally distributed deviations from the power law and throw everything else. Then you get this beautiful, amazing straight line that is almost crazy to see. And so that you can do that. You will do that. But also the other thing, what happens is, it turns out, and then is one of the reasons why the power law works even when you use the least square, is because the deviations go away, right? When you have a peak, you have this very large deviation, and then they correct themselves, so they kind of cancel each other a little bit. It's not exactly like that, but that is one of the reasons why the least square works, roughly. It's not the only way. You can do the others, and then you can show all of them. Here in regression, polynomial regression, I told you what is the main problem is that overfitting, because I can add more and more term, and then I can fit anything. And if you have something that can fit anything, it's like it doesn't fit anything, right? It is not a signal. At that point, you're fitting the noise. There is logistic, so other methods. Just this was mostly to show you there are many methods, and the quantile is just one of them. So guys, if you want to be famous and want to have a lot of followers, why don't you do logistic regression of a power law, and then you call it the logistic regression? Why don't you do the ridge regression of a power law, and then you call it the ridge regression model Bitcoin? It's a new model. It's not. You're going to still applying it to the power law, because otherwise, if you try to do it without that, you will get some stupid results like these ones, right? These are all quantile, but only one looks good. That is the power law. All the other ones are trash, So it's ridiculous, right? How many ways I have to show you that what we are doing is completely stupid, and misleading. And the quantile, right? It says robust to outliers and non-normal data. Sure, okay, because it doesn't really care. It's sorting, right? It's when you do something like that, it's called non-parametric approach. And I have used many of these non-parametric approaches, even for calculate significance, distributions. They are very good when you have data in particular when the data is little, when you have a few samples, you want to use non-parametric approaches because you don't know yet the distribution, or the distribution can be really complicated. But if you have a way of identify the distribution, right? So, for example, in our case, where you say Bitcoin is clearly by model, we can show you over and over. You can do all kinds of tests. You can see it from the distribution. There are two peaks. There is one component where it's really Gaussian, it's really symmetric, and the other one is not. Then you can make, you can improve by modeling the two components differently. You don't have to resort to quantile, or you can apply quantile to the two regimes and see how they combine together. There are better way of doing this. And this is computational intensive. Like, for example, it's very difficult to do this on TradingView. I did it. I was able to do it, but it's really complicated because TradingView has limitations on these computational capabilities. Requires quantile specifications, less intuitive for non-experts. But even for experts, because I know exactly what it's doing, and I have no clue what these lines represent, beside the one below the blue line. Below the blue line, there are all power laws. It's the same power laws that all the other methods find. What are these ones? What do they mean? Can Sina or PlanC give a reasonable explanation of what they mean? They will tell you something. Well, they don't mean anything. It's just some statistical fitting. It's stupid, because we are trying. The reason why we introduced the power law in the first place was to show there is some precise dynamical behavior that has to do to the property of a system, being a network, for example. If you're saying there are a bunch of power laws above it, and they are very different from the below, then you need to explain me what they represent. And I bet they cannot do it, because there is no explanation. In fact, there are no power laws. There are no power laws there. What there is the power law plus deviations, and this deviation decay. And all these can be explained by the dynamic of a system. Yes, there are times where we leave a power law behavior, or more than leaving the power law behavior, there is some additional things happening. There is the price starts to, people get really excited because of the halving or whatever. We go through these bull runs, and then the price corrects, and we go through a bear run. All these things can be explained, and they are in addition. The power law never disappears. It's always there. It's just in addition to the power law, there is this other behavior. And so fitting it with straight lines in the log space is not a good approach. It's I don't. It's a kind of a rough approximation, because this power law being a little bit with less slope, the kind of fakely represents the decay that we observe, but it's not the best way to do it. But it's still useful, because it is complicated to divide it into modes, and then you add some steps, right? And every time you add some step, you can fall in the in a problem that is you're treating data differently, and so somebody can have an objection to it. But if there is a reason, and the reason is motivated by the data, then it's actually the right thing to do, even if maybe the other one is simpler to do. And still you can use it, because you say, look, it's one way of doing it. It has its pro, it has its cons. Let's have 3 or 4 ways of representing the data, and then comparing and see how much we can learn. Because it's almost like, if you go to the doctor will not just take an X-rays, but he will do a blood sample, maybe colonoscopy, whatever other method to see what is going on with you. And, you will not just take an X-ray to see if you have some blood poisoning, right? You will need, if you don't know what is going on with you, I want to have all this information. So it's good to have more than one method. But again, tell people that is a power law, because otherwise you're misleading people. That is my point. So if we want to continue, there are other ways, like the power law. regression. Here, I asked ChatGPT, we were talking about the power law, so he mentioned it as his own regression. It's not really his own regression. It's not a regression method. What you're doing here, you're saying, look, I'm having, I think there is a power law in my data. Take the log of a y, take the log of a x, and then fit that. And you can fit it with least square. You can use Bayesian regression. You can use quantile regression. There are all different ways of showing that the data follow a power law. Now, it is right that because we are transforming the data, there are some possible problem when you do that. One of the things is that you're reducing, and that is one of the criticisms people say, well, you're reducing the deviation because you're taking the log. You need a very huge deviation to see. But that is the entire point. This is what we are trying to do. That is not a bug, it's a feature. We are trying to say, forget about this deviation. It look big and enormous if you're plotting it in a linear graph. But when you're plotting it in a log and you're considering the change in scale. So, and again, if you understand what you're doing, you have to justify why you're doing that. If you're doing it, if Bitcoin went from $10 to 100, it will not be good because to use this method, because it's only one order of magnitude. The fact that Bitcoin went from, basically a fraction of a dollar all the way to 100,000 justify to do that, because you're saying that is what matters. How we went from being a fraction of a dollar to 100,000. Is there a pattern? And the only pattern that matters over many order of magnitude is exactly a power law type of pattern. Because that pattern, if there is a pattern, if there is a proportionality, and that is what a line is, right? It's a proportion, it's a consistent proportion between two things. If there is a proportion, a linear relationship between the log of price and the log of time, it means that what you're emphasizing is the scale. So if somebody says, oh, but taking the log is decreasing the deviation. Yeah, exactly. This is what I want to do. I'm trying to do that on purpose. I'm trying to tell you, if you take a bird eye view, if you're taking a drone and you're looking at the forest, you see a pattern. If you stay inside the forest, you don't. That is the entire point. But it's not really his own regression. This is, Grok saying something because we were discussing it, and so he added to it. But it's better to think that there are all these methods, and then you start with a model that is, okay, am I going to take the linear data? I'm going to take the log of y versus the log of x, and so on. Then there is Bayesian. Bayesian is I love Bayesian approaches. It's basically another way of doing statistics where you basically start with some kind of assumption. It could be even just I don't know anything about this data. I started with a very neutral position, and then as you collect more data, you update. That is another misunderstanding of people, like, oh, you change your model. The problem is not with changing the model. The problem is changing the model, not telling people which method you're using to change your model. Or if your model is so much change that basically shows whatever you were doing before is completely nonsense. If a model is improved over time, and that is okay. But again, you need to explain how this is done, what are the pitfalls of this approach, and so on. And the Bayesian method makes it again like a feature. You say, sorry for the noise outside. It's trying to say, I'm keeping this right of updating my model as I get more and more information. And of course, as always, it needs to converge to something, right? If you don't converge, then probably you're not modeling. There is something wrong in what you're doing, right? It needs to converge to something that is better and better over time. So that is it. I have, among my 13 indicators, I have a Bayesian regression of the power law. Based on the power law, it's still using the log of time and the log of price. And so if somebody does a Bayesian regression, it's not always a new model. No, it's a new way of showing the power law. And then there are other, they are called robust because they are So it's not the only, Quantile is not the only way to minimize outliers. There are other methods where you can minimize outlier and so on. And this is Lasso is more like a machine learning approach. They use kind of almost like an artificial intelligence method, a machine learning method to optimize this goal that is always the same. You're trying to find this general pattern, general equation, right? In the end, you would like to find some equation. Now, it doesn't have to be always an equation. It can be something complicated. But if it's an equation, the beauty of finding an equation, that is the other thing. Like, for example, PlanC was saying, oh, now I'm using network, deep learning networks. First of all, okay, you are asking ChatGPT to write a complicated code that you need to train. It's going to come up with some answer. You don't even know what these answers are because it's some kind of combination of data where weighted in a different way. It's super prone to overfitting. I had the people, I was talking with the head of Walmart one day. It's a long story, but he was all proud of this predictive model. And because at first it looked like, whoa, it was actually predicting every single turn of this. I think we were doing SP500, whatever it is, up and down, it's like, what is going on? And when I look closely, I knew that there was something wrong because you will never be able to do that, right? To predict every single turn and twist in financial data. It was simply the deep learning method he used gave the trivial solution, because if you don't train it correctly, it's going to give you a trivial solution. And the trivial solution was the most trivial solution that you can imagine when you're trying to make a prediction. The prediction was tomorrow's price equal yesterday's price. Basically, it was the same sequence shifted by one. And you could see exactly. You should have been able to look at this and say, oh, okay, I got some stupid result. Let me change something in how I trained this model. But I was completely shocked that he didn't recognize this. Like, what is going on? And I noticed this in many people. This is why always trying to understand what is going on with your data, always trying to go deep in what you're doing, because it could be that you're doing stupid things like that. So again, it's another grift, because if you say, first of all, I don't know of anybody that is using right now deep learning, because it doesn't work. People have tried, and there is it's one of the things that yet doesn't work, right? Deep learning can do amazing things, large language models, all these kind of things based on some derivation of deep learning. But when you're talking about financial data, there is not yet one single paper I read, etc., that it does even a decent job. When it does, like there are some machine learning, for example, Profit from Facebook, it's kind of they claim it's a state-of-the-art machine learning. Machine learning is a more mechanic way of doing some of the things that supposedly deep learning does, but deep learning does it with these networks, right? But it's basically some methods where you're using statistics, and then it's not really like a simple recipe. It's more like something where you have to train a system, and the system over time kind of converges to a particular solution. And many times we don't know how they did that. And you get these trivial answers. But, with deep learning, you use networks that are trying to mimic how the brain works. And they don't work with very complicated things like financial markets. They give you trivial results. Like I said, there is this thing called Profit that uses a little bit of artificial intelligence, but mostly machine learning. And somebody one time challenged me saying, oh, this bullshit power law, let's not use bullshit power law. Some guy that, again, supposedly was an AI expert. Let's use instead a Profit. And when I saw what he showed, I knew immediately that basically was reproducing the power law. And in fact, but it was taking a small amount of data. And then I put the entire data set, and the answer was V power law. That method found V power law. So if PlanC uses deep learning, you can find, my prediction is, I'm telling you my prediction, trivial results like the one that AI Walmart guy found, that is completely nonsense. Everybody can make a prediction, say today's price is going to be tomorrow's price. It's probably one of the simplest predictions that you can make, right? And you don't need AI. Or it's going to find the power law, and he's going to say, "Oh, but he didn't find the power law. Give me the data, I superimpose it on the power law. It's going to be exactly the power law." And it's, again, a scam, because now he's saying that he's using this very complicated method with deep learning, etc., that ChatGPT used for him. So it's actually digging the hole more, because in that case, you're really, if anybody says I'm using this bot is using deep learning, etc., unless there is a real demonstration that is something superior to anything else, and they made a major breakthrough that will make them super billionaire. If he knew how to use deep learning to predict prices, he will be a billionaire in very little time. Otherwise, it's a scam, So don't trust it. So it's one more evidence that something is going on there. That I don't like it. But anyway, so hopefully I gave you an idea of how these methods work, what they do, why, if you don't specify what you're doing, quantile means nothing. Hopefully I made my case. So I'm going to see if there is any questions at all. Okay. I don't know. Arbitrage, yes. So this comment was when I explained how people could make money by taking advantage of the different values of Bitcoin in different exchanges. Some people still do it, but that arbitrage difference is so small because people took advantage of it. So there is very little left. Right. So there are different apps that is another thing that eventually we could do, because maybe there is something. It will be interesting to show different power laws. Never done it on different exchanges. Do they change? Do they show different slopes? Can we learn anything from that? That will be an interesting study. Is there anything to learn by plotting power laws? They will all show power laws, but maybe with different slopes, etc. Maybe there is something to learn there. Could be interesting study to do. With cost and stuff like that, so you can see the amount of profit you could make. Yes, if you want to do arbitrage. Yeah, but then you have to execute it. It's not trivial. I know that there were people that were making a lot of money, so in the early on, but now it doesn't work very well, I think. Or it's very tricky to do it. I think people need to be educated that even Bitcoin, where to go exponential, doesn't validate. Yeah, so whenever people say that, right, my answer is always, it has already done it 4 times. Every time we had one of these bubbles, the price went kind of exponential, and then it went exponentially down, almost in a symmetric fashion. Look at these bubbles; they look almost like triangles, right? Equilateral triangles, or isosceles, where we went up in the same way we went down. And so in average, the power law is that. Now, and that is another thing I differ with PlanC, because one time I heard him say, well, what if a cycle, for cycle means whenever we leave a power law, right? Because the idea is that we stay at the core for 2 years, and then, at least in the past, we spent 2 years in this turbulent region. If that doesn't happen anymore, right, because that is still the big questions. Is the cycle broken? It's not broken. It's still there. It's still an open question, because we are seeing the price correcting. What is different once we usually leave a reference line, we almost never go down that reference line for 2 years when we are in this other regime. And this time we stayed below the power law very slightly, but we stay there for a longer period that we ever done before. So that is different. But we could recover. The price could still go to 200,000. I don't think we are going to revisit this 95 quantile. So if you look at the quantile model, 200,000 is more like what, 85 quantile or something. We can look it up maybe. I have my own version of the quantile model. In fact, I can show you, can share it with you. So right now, let's say it's 6 months from now, right? So basically by the end of the year. So 200 is more like maybe 90 quantile. So, and it's very big difference because by the time you go to 95, we're talking about 235. So 190 is more like 189. So close to 200. So it's possible that we go to 90 and it will be really already an extreme. But I 95, because I told you it's kind of overestimated. Yes, in the past 95 represented close to where the peak was, but because of these power laws, not exponential, because the decay is more like an exponential. They don't represent well the decay, and so 95 is something that probably we're not going to revisit. But imagine the cycles were not there, and we went up exponentially. We are not going up exponentially. If anything, we are following. We are following even more than ever the power law. That is the problem, because I would like to see myself for 1 year, going to Cancun. Like I say, we are going to Cancun, and then we come back home. I would like to go to Cancun with Bitcoin to 200K. Right now, we are staying home. Like tariffs, etc. People, Bitcoin say, I'm not going anywhere. If we follow the power law, then we follow the power law. So they don't even matter, these quantiles anymore. We have simple small deviation along the power law. It could be, right? But imagine we go exponential, and then it lasts more than a year, then it lasts 2 years, then it lasts 3 years. I will be the first one to say, no, it's not a power law anymore. It's following an exponential, and there are ways to tell. And it will be dishonest to say, well, but what if in 4 years from now we go back to the power law level? All right, when that happens, then we will have to figure out what happened. But I will be there, the first one, to say, well, we are not following the power law anymore. It will be dishonest. It will be not a good scientific way of analyzing the data if you made claims like that, right? And this is one of the things I heard from people that say we don't have cycles anymore unless we follow the power law. If we don't have cycles, then, and we start to do weird things, in both directions. It could also go down in an exponential fashion. People never consider that. So I'd rather see what we saw before in the cycles, where we leave a power law, we reach a peak, then we go back to it. Oh, we follow the power law. If we start to go exponential, I will be worried, because I mentioned many times how exponentials are unstable, and then they crash, and we add the evidence of these for every bubble. But they went up, they crashed, but because we went up in a limited fashion, they crashed and corrected, and everything returned to normal. If we had 4 years, 5 years of an exponential behavior, and not slow exponential, very fast exponential, I don't know, it could be maybe even not good for the system, so yeah. How can we tell if we are not at power law anymore or whatever? We can discuss it. That will be a good, interesting things. Yeah, thank you. Sorry for my videos are a little bit too long. The entire idea is to go a little bit deeper and understanding these things that other people many times don't do, because we are trying to be sensational or to be appealing, etc. I want to focus on understanding, and I think people say I tell people they are stupid, etc. No, most of the time, if people want to learn, I encourage them. I'm a teacher, I support them. I am mad sometimes with with trolls that don't want to learn, they are not interested, and many other people just dismiss the troll, they don't even talk to them. I am in their face. I don't know, maybe that's a stupid thing to do, but why? Because I hope, even I know it sounds absurd, but I hope the troll, if I shake the troll, maybe the troll wants to learn. Maybe I don't know, maybe I'm too crazy to think that, but that is my idea. If I simply dismiss it, there is not an opportunity. Maybe if I challenge him, maybe he turns around. I don't know, But yeah, I do things in a slightly different way. Hey, Sander, nice to see you. Sander is such an amazing guy. 420, yep. I don't use much of it stuff, Maybe I should. All right. Yeah, I mean, it did it right for every, and Bitcoiner is almost like Bitcoiners is teaching us a lot of things through its behavior, right? It's saying, yeah, I can do the exponential thing, but over a long period of time, it's not good thing. So I'm correcting myself, right? So there is a reason why and this, when say Bitcoin, right? It's not like there is an entity called Bitcoin. That entity is us, it's a network. It's a wheel of many people interacting with each other, and there is wisdom of a crowd. That is what Bitcoin manifests, the wisdom of a crowd. And there are other systems that show the stupidity of a crowd, right? Bitcoin shows the wisdom of a crowd for whatever reason, because of its nature, how it works, etc. It manifests the better properties of all of us, right? Question: what do you think about swipe and sharing Bitcoin ETF and not holding any actual Bitcoin? It's a great tool. I have myself. One of the reasons is because you can, for example, you can do retirement account, right? One of these um, self-managed accounts using Bitcoin. There are some companies that allow you to do that, but in my use of Robinhood, I can buy easily Bitcoin in your same mining, right? But in general, ETFs, right, even the spot ETFs that we have right now, are good tools because you can use them for your retirement. You can do Bitcoin, but it's more complicated. For tax reasons and things like that, right? The mining ETFs, I know they were very popular before all these other ETFs came. I started to analyze the mining companies, and I want to understand them better. I did it with MicroStrategy, right, where I show there is like a power law between MicroStrategy and Bitcoin. So that explains they can model the leverage that MicroStrategy has. I want to do the same thing with the ETFs, the mining ETFs, but I didn't have a chance yet. I like mining. I think Bitcoiners should support mining because it's at the core of what Bitcoin is. So anything we can do to support mining, we should. So if it is another way of expressing support for the entire network, including Sailor, this is one of the reasons why I do have some MicroStrategy trades shares, because I want to support what he's doing. I don't agree with what he does all the time, but I think he has an important role in the system. And so, independently from, of course, we want to make sure it's a good investment, but Yeah, why not? But I want to understand better the mining stocks. I didn't study them yet. Yeah, I like Grok. I studied. I loved early ChatGPT, but then it seems that they're making it worse over time instead of better. Uh, okay, you will disappear on a sunny beach somewhere. I don't know. Yeah, so that is the other. That is the other. How do you call it? So there are some people. Um, Ben Howen, for example, he uses the power law, and he uses the power law after I discovered it, and he calls it the log curve. I think it's exactly because of that, and it's not just my paranoia. Because he doesn't want to call it power law because somebody else made the power law. And it's not my paranoia. Let me tell you, without revealing too much detail, that actually some people that work with him, they were actually in his inner circle, they actually contacted me and they said exactly that they were kicked out from his um, organization and they were part of it because they mentioned that. They say, it's not this, the power law, because it's actually one of the things that Ben uses all the time, this log curve. It's absolutely the power law. It's because it's log curve, it's a log of a price versus the log of a time. He displays it like this, like you're seeing in the upper graph, where first he feeds using the log of a price and the log of a time, and then you can show it in a log linear chart, and it will look like this curved graph, but there's nothing else than the power law. Again, somebody else that you, and it's no problem. Use it, of course. It doesn't belong to me. I don't have a patent on this thing, you know. But if you don't tell people, then people ask this question and they are confused. They don't understand it. And from what I understand, he even block people. If you say it's not this the power law, he blocks you. This is what I heard. Maybe you guys can confirm me. And many people think this guy is this amazing analyst, etc. And he's good. I like some of his analysis. I think he does too much TA sometimes, and I don't like TA. But he's an engineer. He called this series "The Beauty of Mathematics" or whatever. So I will not have a problem with him at all. But I do have a problem with this because, in particular, if people ask you, "Is this the power law?" and you say, and you block them, is that true? Can somebody confirm that? Because I know that this guy that was working with him, basically, he got kicked out uh, because he mentioned the power law. He say, are you not doing the power law here? And he got kicked out. Is that true? Because it will upset me if people ask him, is this the power law? And people get blocked. Maybe you can tell us, if that is the case. Yeah, so that is what it is. All right. So the key to be a teacher. I love it. I love to be a teacher or to try to be a teacher. It's a role, right? We all play roles in life. One day you are a teacher. I'm learning from you. Today I am the teacher. We learn from each other. And that is one of the most magnificent things about being a teacher because you learn. It's one of the best things. When I was a professor, I will wake up every single day and I thought, this is amazing. I'm getting paid. I was not getting paid a lot, but I'm getting paid to teach stuff that I loved since I was a little kid, and I thought it was like an incredible thing, and I never I will never miss the job, unless I was sick and making other people sick. But I will wake up and feel supercharged to go and teach. And there are the equivalent of trolls. There are students that don't like you have an accent. There are students that don't want to learn. But the majority, they were good and they liked me. I put a lot of time, I had extra hours beyond my office hours, trying to communicate with the. I have still some students that are friends after all these years, and they follow me online and we talk. It's an amazing thing, and this is one of the things that motivates me to be online with you guys, because in the end, sure, it's my job, but is why I have indicators, etc. Is the way I support myself right now. It's my full-time job. It's I could do 100 things. I have received offers of all kind, but I'd rather do something that is related to teaching and sharing information. I need to pay bills, but I prefer making a few $1,000s and then sharing this content with you and learning together than doing other things. So that is one of the motivations and this is why I get upset sometimes. I know I don't do it in the most let's say social acceptable sometimes way. I get mad or whatever, but to me, in the end, these things matters. Communicating the right information to people, it's important. It's why we should do these things. That it's not about getting clicks or clout. It's about sharing knowledge. Anyway, hopefully this has been a useful discussion and you learned something. We can revisit because I want to go a little bit deeper and I want to show you the Bayesian model, what we can learn from it. So one thing we can do next time is different models of a power law using different regression and compare them and say, what can we learn from this? What information can we extract? So that could be an interesting discussion. All right, guys, I'll give you a hug, everybody, and we'll see you soon.